In this video, we will cover 6 different techniques to measure the performance of a classifier model. Now, just to recap, a classifier is a machine learning model that is able to make predictions based off of discrete categories. So an example of this could be a model that can make predictions based on whether an image is either a fish or a turtle, or we have an image of a dog or a cat. Something where we're talking about discrete categories. Now, before we dive into our 6 different methods, let's first make some quick definitions that will help the discussion later on. Okay, the first thing that I want to make note of is that although in general a classifier can deal with problems with any number of classes, to simplify the discussion here, I'm just going to consider the case where we're dealing with data with only 2 classes. Those classes can be labeled as 0 and 1 to keep things simple. Beyond that, let's define 4 terms. So the first is a true positive. And this is the case where a classifier correctly predicts a positive result. So in our case, it correctly predicts a 1, where the true label is also a 1. Now, a false positive is where a machine learning model predicts a 1, but the real value, the true value, is a 0. So that's a false positive. A true negative is where the machine learning model will predict a 0, and the correct value is also a 0. And a false negative is where the machine learning model predicts a 0, but the true value is 1. So let's just keep that in mind while we work through the following definitions. So the first measure we will talk about here is accuracy. Now, accuracy measures the fraction of correctly labeled samples in our data set. And computing accuracy is pretty straightforward. So what we do is we take the number of true positives plus true negatives and divide that by all the samples that or the number of samples that we have in our data set. So that's the sum of the true positives, false positives, true negatives, and false negatives. So this is something that is fairly intuitive to compute. However, there are cases where the result that we get from computing accuracy can be misleading. And this will arise in the case where we have unbalanced classes in our data set. To look at an extreme example, we can consider the case of anomaly detection, where, say, out of every 100 samples, only 1 or 2 will have a class that differs from the majority. In this case, a classifier that's trained on these data could simply learn to give the majority class label, and that will cover about 98 to 99% of all the data that we have. Superficially, that will look quite impressive. However, for our purposes, it's actually not doing much good at all. So that's why we need to look at other measures as well. And take note here as well that ideally the accuracy will have a value of 1. That's the best possible value you can get. And the worst value that you can get is 0. So the second metric we can talk about is precision. Now, precision measures the ability of the classifier to correctly label positive values. We can take a look at how to compute that. So that's just the number of true positives divided by the sum of the true positives and false positives. So here we are simply getting a measure for our classifier's ability to correctly identify all the labels that are labeled with a 1 in our case. Like with accuracy, precision has a maximum or an ideal value of 1 and a minimum value of 0. Recall is the third metric we are considering. Now this measures the ability of the classifier to find all positive values. So all classes, or all samples that are labeled with a 1 in our case. Now recall is computed by taking the number of true positives and dividing that by the number of true positives plus false negatives. And so this is just telling us how close does our classifier get to correctly labeling all of our positive cases. So like the other two metrics before, in the ideal case, we have a recall of 1, and well, the worst possible case is that we have a recall of 0. The fourth measure is the F1 score. Now the F1 score is simply a weighted average between the precision and recall. We can compute it with this equation, and the F1 score is a fairly standard measure to use when evaluating a classifier. So it's quite common to make use of this. Like before, the ideal case is that we have an F1 score of 1. The worst case scenario is that we have an F1 of 0. The fifth technique is actually a visualization method that we can use to evaluate our classifier. And so this is the ROC, or Receiver Operating Characteristic plot. Now this is a way to visualize the diagnostic ability of a classifier. We could take a quick peek at what this plot actually looks like. And here you see it. On the horizontal axis, we have what's called the false positive rate. On the vertical axis, we have the true positive rate. Now both of these are given by these following equations. You can see that the true positive rate, or the TPR, is actually the same as the recall that we discussed just a moment ago. Now what's going on here under the hood is that we are actually evaluating our classifier for different threshold values on the raw model output. Now what do we mean by this? A classifier does not output a nice, neat class label from its output. What typically happens is that our model will output a probability. It outputs a probability that a sample belongs to one class or another. The way we convert this probability into a class label is by using a threshold value. Now, normally the threshold value is just 0.5. And so any probability that's above 0.5 gets labeled to class 1. Any probability that's below 0.5 gets labeled to class 0. Now this threshold value is just set, but we can change that, we can tweak it, and for any given problem it could be that a different threshold value is actually more ideal for the problem you're dealing with. So what's happening here is that we are altering the threshold value, and the threshold value is being changed from 0 to 1, and the classifier's performance is being evaluated through the true positive and false positive rates. Now the model performance is actually indicated by the blue line or the blue jagged line that you see in the upper left-hand corner of our ROC plot. The orange dashed diagonal line represents random guessing on all of our samples. So in general, the higher up our blue line are towards the upper left-hand side of the ROC plot, the better it's performing. And that's exactly what we want to see. The closer that blue line is to the diagonal, it means that the classifier is not doing much better than random guessing. And if it's below the diagonal, then in fact it's doing even worse than random guessing, and we have some big problems. So this just gives us a quick way to visualize and see how well our classifier is doing. And it's worth pointing out that the ROC plot is really meant to be used with binary classification problems. Now, the sixth and final method I'll cover here is the confusion matrix. And this is just a tabular illustration of the true positive, true negative, and false negative counts. So we can take a look at an example here, again for the binary case. And what we see here is a box that's divided up into 4 quadrants. We have on the horizontal axis the predicted label from the classifier. The vertical axis has the true labels of our data. And what we want to see here is all our data samples falling into the diagonal of this plot. And so that's the yellow and green squares that we see here. You can see that in each quadrant we have a number, and that just represents the number of samples that fall within that quadrant. So the ones that fall within the diagonal have been correctly labeled. The ones that are off the diagonal show where the model has made mistakes. So this is just a quick way to size up and see how well our classifier has done. And so this concludes the video. If you'd like to see all of this content being discussed in a blog post, I have a link to my post that this video is based off of in the description below. In that post, I also go through some Python examples where I work through some of these concepts in a bit more detail. If you got some value out of this video, please like, share, and subscribe, and I will see you in the next video.